very much for the introduction. So my talk is going to be based on work that we did here at the AEI in the geometry and gravitation group, together with Lars Henderson, Jeremy Jodiot, and some other collaborators as well. Okay, so while the title might not suggest it, my talk is mainly going to focus around the propagation of light in curved spacetime, and I hope I'm going to convince you about this in a moment. Okay, so let's start with some basic facts. So in general relativity, the propagation of electromagnetic waves is often considered using the geometrical optics approximation for Maxwell's equation. And what we get from this approximation is that light rays follow the null geodesics of the underlying spacetime. And we use this approximation to make most of our astrophysical predictions. Okay, but now the problem is that geometrical optics is valid only in the limit of infinitely high frequencies, and we know that the radiation that we observe is a finite frequency. So then there is the question if we can do better than this, if we can come up with a better theoretical model for describing the propagation of light in spacetime. Okay, and my goal today will be to present to you such a model where we are going beyond the geometrical optics approximation by including higher order corrections. And in this case, what we obtain is propagation, that the propagation of electromagnetic waves becomes polarization dependent. And
I have a question here. What exactly do you call geometrical optics? Is this just geodesics, or you're thinking about iconal expansions, or what's
it's just the geodesics.
Thanks.
Okay. And this is what we considered in the papers mentioned over here. So extensions of geometrical optics for Maxwell and linearized gravity. And by doing this, we obtain the following. So the dynamics of polarized wave packets is effectively described by massless spinning particles. And these particles deviate from the usual null geodesics that we have in geometric optics. And just to give you a feeling of what this effect looks like, let me give you a very brief example. So here we consider a Schwarzschild black hole, and we consider here some source of radiation far away from the black hole. And now if we emit a null geodesics from this source of radiation, we see that the null geodesic will remain in the equatorial plane of the Schwarzschild black hole, and we will get the ordinary light bending for null geodesics. Now, on the other hand, if we consider the equations that we obtained and we consider circularly polarized light, and we do the same, we look at similar trajectories, what we will get is that due to the polarization, this light rays will get deflected off the equatorial plane, and in the end, we'll have this finite deflection angle off of the equatorial plane of the null geodesic. And this also will depend on the state of polarization of light. So this is basically the spin Hall effect of light in Schwarzschild in a nutshell. Okay, let me go on. So another important point that I want to emphasize over here is that the energy centroid of polarized wave packets, or in our effective description, the position of massless spinning particles is observer dependent. And this effect comes into our equation of motion and plays a very important role. Before going further, let me tell you a bit more about this observer dependence of the energy centroid of wave packets. And I'm going to start this with using a simple mechanical model. So for example, here, I'm considering a spinning wheel, which is located in the XY plane, and the angular momentum is directed along the Z-axis. And on the left, I have an observer which is at rest with respect to the axis of the wheel. And this is how the observer sees the wheel here on the left. And now, on the other hand, if I boost this observer with some velocity along the x-axis, what the observer will see is presented over here. So the wheel gets contracted along the x-axis. And furthermore, because the wheel is rotating, the energy center of the wheel gets shifted along the y-axis. So the observer will not see the energy center at the center of the wheel, but it will see it displaced along the y-axis over here, depending on the rotation of the wheel. Okay, so now we can extrapolate this this classical model, and we can replace the wheel by an electromagnetic wave. In particular, we can replace the wheel by a circularly polarized Gaussian beam. Here, what we see here on the left is the 0-0 component of the energy momentum tensor for such a circularly polarized Gaussian beam propagating in the z direction, as seen by one observer. So we see that it is perfectly symmetric in this case, and the energy centroid will be at the center of the xy plane. And now the question is, what happens when we boost this observer along the x-axis? So the boosted observer will see a deformed image like over here, but most importantly, the boosted observer will see the energy centroid of the Gaussian wave packet shifted along the y-axis, depending on the state of polarization of the beam. And this polarization-dependent displacement, delta y, is called the Wigner translation. So more about this can be found, for example, in this paper or in many other papers in the literature. Okay, so with this in mind,
sorry, only a remark. Is this only true for me? But I cannot see the bottom lines. So the references you are referring to do not show up on the screen.
I don't know. So does anyone else see the reference?
No,
I
it's working fine on mine.
It's only for you.
Okay.
I can see them.
So let me take this opportunity to ask a question. So
Okay.
how are these pictures obtained? Is this what kind of model is that, or is this an observation?
So this is a theoretical description. So for example,
what? A scalar wave or what?
no, it's an electromagnetic wave in the paraxial approximation, and it is circularly polarized.
Okay. Thank you.
Look at the 0-0 component of the energy momentum tensor in this plane.
Thank you.
So now let me continue and give you a brief summary of how we derive the equations of motion describing the spin Hall effect. So our approach is based on the WKB approximation. So we start with the WKB ansatz for the electromagnetic potential, as shown here in equation 1, where we have the WKB expansion parameter epsilon. So for the sake of simplicity, we can roughly think of epsilon in this case as representing the wavelength. Okay. So now what we do is we take this ansatz and we plug it into Maxwell's equation and the Lorentz gauge condition, and this is what we obtain over here. So we obtain that the gradient of the phase represented here by P is null, and that P is orthogonal to the polarization vector A0, and also that the polarization vector A0 is parallelly propagated along P. Okay, so based on this orthogonality relation between A and P, it is convenient to rewrite the polarization vector in terms of a null tetrad. So we can write it in terms of vectors M bar, which are orthogonal to P, and also in terms of P over here, where Z1, Z2, and W are complex scalar components. Z1 and Z2 will describe the state of polarization of our WKB ansatz, and the component proportional to P is a pure gauge component which will not play any special role later on. Okay, but now in order to be able to fix M and M bar, we need to introduce some additional structure. So it is not enough to use just that A is orthogonal to P. We need to introduce either another null vector N or another timelike vector T. So in this sense, M and M bar will always be functions of P and the timelike vector T. Okay, so this is already anticipating to some extent the role of an external, of the choice of an external observer. Okay, so I'm going to skip the details and go directly to the final result, because this WKB ansatz would take us a lot of time. And what we obtain in the end are the equations of motion describing this gravitational spin-Hall effect. Okay, so we have here the equation x dot and p dot. And if we look at the first terms over here, these are just the null geodesics equations. But on top of the terms which gives us null geodesics, we have some correction terms of order epsilon. So first order in wavelength, basically. Okay, and these correction terms depend on m bar, and also on our external choice of timelike vector field t. So basically, the correction terms will always depend on our choice of an external timelike vector field t. Okay. We also have another equation z dot, where z is a complex 2 vector. Basically, this is just another way of rewriting the parallel transport equation for the polarization vector in terms of what we call a Berry connection B. I'm not going to give the details of how B is defined because it's not really necessary for this talk. And also we have a constant of motion here, S, which is basically the helicity of our wave that we are considering. So we have S equal plus minus 1 for circularly polarized electromagnetic waves, and we have S equal plus minus 2 for circularly polarized gravitational waves. Okay.
So can one not just choose the vector t to be parallelly transported along p?
The choice of t is arbitrary.
Yes.
It just needs to be
so why not set this set the derivative of t with respect to p 0?
So choosing a particular t is just a choice of family of observers which would describe the motion. So it doesn't make sense to pick one particular t as special. So there could be an observer which describes the same motion, and it would see it slightly differently. I'll try to show this with some pictures in the following slides.
I'm really perturbed by this. So this is, what does this equation of motion represent? The center of energy? Is this what's happening? Or I mean,
yes,
when you have a wave packet, you need to say which
so
part of the packet you want to describe.
Yes, exactly. So this will be, I think my examples that come in 2 slides will clarify.
Okay, thanks.
Okay, so before going to the examples, I have one more remark. So our equations can be put in a form which resembles the well-known Mathisson-Papapetrou-Dixon equations. So in order to do this, we just need to define a spin tensor as over here, either in terms of m and m bar, or either directly in terms of p and our choice of external timelike vector field t. Then the equations can be rewritten as over here, where equation 9 and 10 represent the actual MPD equations, and the equation for x dot can be obtained from this MPD equations by imposing the spin condition S contracted with t equals 0. So in the language of MPD equation, the choice of timelike vector field t would to some extent fix our choice of energy center of the beam. Okay, so now let me go to an example, and hopefully this example will help clarify some of the things. So given the equations of motion, the most basic example that we can look at is Minkowski spacetime. So in Minkowski in particular, the equations simplify a bit. So we have basically geodesic equations plus a correction term over here in the x dot equation, which explicitly depends on the choice of external timelike vector field t. So now we can just make different choices for t and see what we obtain. The most obvious choice would be to choose t as the standard observer in Minkowski, in which case this second term is 0 and obtain null geodesics, regardless of the value of epsilon or s. The second possibility is to choose some family of boosted observers. So, and here I have t prime as one example, which is a family of boosted observers along the x-axis, where the rapidity of the boost is parameterized by the time coordinate in Minkowski. And in this case, the correction term over here is non-zero, and what we obtain are polarization-dependent trajectories. So let me plot you these trajectories, and hopefully this will start to make things a bit more clear. Okay, so first choice of observer T, we just get null geodesics. So if we start here at the origin of Minkowski spacetime and we have a ray going initially along the z-axis, this will be a straight line in Minkowski. This is just the null geodesic that is seen by this family of observers over here. Okay, now on the other hand, if we look at solutions of the equations as seen by this other observer, T prime, which is the boosted observer in the x direction, then we see some polarization-dependent corrections. And instead of a geodesic, we see these different curves over here. And here we have a displacement between the trajectories seen by T and by T prime, which on one hand depends on the helicity, it depends on the wavelength, and then it depends on the magnitude of the boost of the observer. But as we see over here, delta y will be limited by the wavelength, so it cannot be greater than one wavelength in this case. So basically, what these equations are reproducing exactly this Wigner translation for Gaussian wave packets that I mentioned in the introduction. So the boosted observer will basically see the trajectories slightly displaced as compared to the standard reference observer over here. Okay, so this is what happens in Minkowski. We can also look at a more complicated example. We can also look what happens in Schwarzschild, for example. And here we have the Schwarzschild metric, and we can pick two different observers in Schwarzschild and see what we get. The choices that I made over here are the following. So on one hand, let's say as a reference, I picked a static observer T. And as a second observer, I'm picking a free-falling observer T prime, given over here. And now I can take these two observers and plug them into the equations of motion and see what I get. And the result is, it's more complicated, obviously, but it's very similar to what happens in Minkowski. So with green, red, and blue, these are just the trajectories that I showed you in the introduction. Now, we can compare this with the trajectories seen by the T prime, by the free-falling observer. And you can see here with the dashed lines are slightly displaced when compared to the solid lines. So this is basically a generalization of the Wigner translation that one sees in Minkowski to the case of the curved spacetime. While in Minkowski, I was able to say that the displacement is always limited to one wavelength. Here in Schwarzschild, I'm doing a numerical simulation, and I'm not, at the time, I'm not able to say this analytically, that the displacement is still limited to one wavelength, but this seems to be the case nonetheless. Okay, so let me conclude my talk. So we provided a covariant framework for describing the spin-Hall effect, as well as the observer dependence of the position of massless spinning particles. So our equations of motion reproduce the effect of the Wigner translation in Minkowski, and they also provide a generalization for this effect in curved spacetime. Okay, so now with this theoretical framework in mind, what we aim to do is to focus on astrophysical applications to see what are the implications of our equations for various applications, such as gravitational lensing, black hole shadows, or wave optics phenomena in astronomy, for example. These are just a few examples. One can go beyond this list. Another interesting possibility, which would involve experiments on Earth, would be the following. Are Wigner translations experimentally observable? Even though this is a sub-wavelength effect, weak quantum measurements, for example, can in principle detect such displacements, and this might be a possibility. Okay, thank you very much for your attention, and I'm looking forward to any questions.
Well, thank you very much for this clear talk. Well, just one very quick question. So the necessity of introducing this observer is related to the massless nature of Maxwell field, right?
Yes, exactly.
Okay. Any more questions or remarks?
Bobby, there's a question from Gautam from the
Yeah.
audience.
Yeah,
Yes,
can you hear me?
Yeah.
Yes.
Okay, so first, are your equations exactly equivalent to the Papapetrou equations? Is there no, I mean, and then second, I mean, I think you did mention this on a slide, so I may have just missed a particular point, but those equations require this spin supplementary condition that you had before. Is that derived from your, you know, WKB type approximation,
Yes.
or is, okay, I see.
Yeah, so we're doing the WKB, we're deriving the equations over here that you see in 4, 5, and 6.
Right.
And by just rearranging the terms afterwards and defining the spin tensor as over here, we obtain this form of the equation, 8, 9, 10.
Is this form of the spin tensor the most generic form of the spin tensor that you could write down from the Papapetrou, or is this a specific kind of, you know, spin tensor that, you know, that is coming from your analysis?
No, this is coming from our analysis. And then we just observe that equations 8, 9, 10, which are our equations, are equivalent to the MPD equations with this supplementary condition as contracted with t equals 0.
Thank you.
Okay,
So there's a question
else?
from Thomas also.
Yeah.
Yes, so I would like to know whether you can somehow assess the quality of your WKB expansions, because I'm aware of some analysis, at least, which says that the standard WKB expansion without spin effects for just Eikenall equation and transport equation for the amplitude are at least asymptotic solutions to Maxwell equations in certain cases. Can you say similar statements about this spin-dependent expansions?
At the time, I can only make the speculation. So we didn't made any quantitative assessments of this. But I can only speculate. But that by including higher order correction terms, you improve the limit of validity of your model.
Okay, thanks.
May I just make a comment on the supplementary condition? As far as I understand it, I mean, this simply states that there's only spin present and, so to say, no boost component in S for the observer T.
Yes, yes.
Okay. Well, I think, yes, we can now move on to the last talk.